Hey, John here. Let's look at this FPGA breakout board design. As always, I'd like to thank all my Patreons first and foremost. All right, especially the VIPs. You really help defray the costs of my mistakes and learning and the evolution of all this stuff. Thank you very much. So let's first understand the motive of why this board even exists. Why don't I just go out and buy something else? Well, we're going to look at the schematic in a minute, and we're going to see that what my motive was for this particular board design is that I wanted as many pins as possible, if not every single one, connected out to these headers. I don't like it when you go out and buy, an FPGA eval board, and, 10 years ago, they would be just loaded with all kinds of parts to evaluate. That's fantastic if that's what you want to evaluate. If you want to evaluate the FPGA itself and not have anything in the way and interfering with all their pins, you want the exact opposite of that kind of an eval board. And for this particular chip, the only one that I knew of at the time, this is, 4 years ago, as you can tell, I started it in 2019. They had, a lot of pins already committed to other things, and there weren't that many broken out. So I decided I'd just build my own. Ultimately, I was going to do that anyway. I wanted to build something with an FPGA in it. I need to make sure that I knew how to actually build something with an FPGA in it. So this was the first time that I actually did that. Usually I would just program up a eval board and plug it into something that I'd built and so on. But in this case, I wanted to use the whole chip for my own purposes. So the point is, as much as possible was broken out of this chip. Originally, I didn't even have these LEDs in here, which you could argue are already interfering with pinning out every one of these chip pins to these headers, okay? Now, these are passive parts. You don't have to populate them, was what I was thinking when I put them in there. And I added them, of course, because every time I built anything, I needed LEDs. And what I would do is I'd put a breadboard over here, and I would always have rows and rows of discrete LEDs and resistors and stuff in them. And I thought that was just foolishness. So I went ahead and stuck LEDs on there and just said, the heck with it, I need these. I also wanted some push buttons so that I could create some user signals, again, without having to hook a bunch of wires up. And also, again, you're free not to put these in if you don't want these parts interfering with the signals on the FPGA. Because the same pins, you can see these numbers over here. It says like 105 and 102. If you look around here, you'll see 105 and 102 are like right over here. So it turns out that the same pin signals that go to these switches also go to these header pins over here. In fact, that's why these are an italic font over here. We'll look more closely at the board layout in KiCad in a minute, and I'll explain how all these little features manifest themselves, all right? So if you're going to use this board or want to follow along the schematic, you understand why I did things the way that I did. First and foremost, the motive was, if I want every single pin uncommitted and connected to these headers, and I got that. I believe I achieved that goal. I also said, well, I'll cave, put some parts in here. If I want to solder them in so I can have LED indicators and push buttons and things like that. Now these headers over here are pinned out to plug into a Raspberry Pi. This one on the far left is the one that I usually plug directly into the Raspberry Pi. Quite often I also want to probe around and look at the pins on the Pi. If they're already committed to this header, then I need a way to clip a probe on, so I put another one right next to it, and I labeled it because I can't stand looking up all the freaking pins and junk in the Google search on what the heck is the pinout for the Raspberry Pi, where is GPIO 18, and so on. So I found that useful. These things that have the white boxes around them are extended over to this header here. So if you're just picking up random pins and say, oh, I just need a GPIO to do some random thing with, don't choose the ones with the boxes because they're talking to the FPGA, all right? And these connect to the FPGA by way of this header here. Depending on how we put the jumpers on this header, the Raspberry Pi, through its SPI interface, when select CE0, can talk directly to the FPGA and program it without even using a flash chip. We'll look at the Git repo in a minute, and you'll see in the revision history, it wasn't until, year number 4 of me using this board that I even included a flash chip on here for the FPGA to boot itself. And that's because the whole purpose of this originally, back in 2019, was to design boards that had FPGAs on them that were meant to go on a Raspberry Pi, where the FPGA was just a coprocessor of sorts, right? Or, a really intelligent peripheral. Why waste my money on a flash chip and all the board real estate to hook it all up if it's plugged into a Raspberry Pi anyway? Just let the Raspberry Pi program the FPGA directly. So this was the original idea behind this particular Breakout board. And as you can see with all the dates on there, it has evolved since to do a little bit more. Okay, bird's eye view of the whole thing. See these big yellow boxes up here and this one here. Combined, they represent all the pins of the FPGA itself. Now at 144 pins, I'd have to make a part, half the size of this sheet to have the pins go all the way around the outside, just to have it on the drawing. This is very common that when you see these FPGAs and other large parts drawn, they draw them in sections like this, okay? So what we have here is power, clock, and reset logic over here. And each one of these 4 boxes here represents one I/O bank each. Okay, so each one of these you'll see VCC I/O 2, 3, 1, and 0. Okay, well, of course I could have put them in order, but I didn't, but so be it. Now, as I had mentioned before, when we were talking about the HX, ICE40HX chips, each of these I/O banks can have a different power source, different power voltage, and therefore, as you can see in the schematic, they all have their own power input connector in here. Now, in this particular board, all of them are connected to 3.3 volts. I'm not getting cute and running one of these at 2.5, another one at 3.3, and another one at 1.8. You can do that in more advanced projects, but this is a single voltage project, and everything's running at 3.3. So, number 1, all I/O banks running at 3.3 volts. Let's look at the reset and configuration logic over here. This also is running at 3.3. For the SPI, I think that's mandated. If you look through the data sheet, the SPI must run at 3.3 volts. And then you have some weird voltages. The VPP 2.5 is the voltage that's used to program the non-volatile configuration memory that I never use in a hobby project. It's one-time programmable, so it's not of any real value to me. I think if you read the data sheet closely, if you want to, you could just hook this up to 3.3 volts, because I never really use it, because it does say it can run at 3.3. However, the evaluation board from Lattice that has an ICE40 chip on it uses a circuit like this to drop the voltage down a little bit. We put in a regular old signal diode here, a 44, 1N914 style diode, and it's going to drop your voltage by about 0.6 volts or a half a volt or something like that. So the 3.3 volts up here end up coming out around 1.7 or so, which is in the range of the tolerable value that it's really supposed to be. So this takes care of that. I threw a little capacitor in here to stabilize it if this thing has some varying current draw and stuff like that, just a little local bypass, okay? VCC on the HX40 must go to 1.2 volts because the inside of the chip runs at 1.2 volts. This is the power that runs all the LUTs and everything inside the FPGA. So it has its own power supply, and it has to be 1.2. You have no options. This here is for, testing or something like that. The data sheet says do not connect it, so I did not connect it, okay? What else is going on down here? When you program an FPGA and it comes out of reset, one way or another, when it's done programming itself or you're done downloading code into it using the SPI bus that I pinned out right here, okay? This signal here goes active. says, okay, I'm done. Quite often there's an LED on here, and honestly, I probably should have considered doing something like that here as well. I mean, after all of this is an eval board, and not having an LED on here, it can be annoying when you're, don't realize how if you're trying to program it and it doesn't work. It would be nice to have an indicator on there. So maybe your Rev 4, we can add another LED. Nonetheless, what happens is when the chip is done configuring itself, programming itself, and it starts working and running the application you put into it, this signal goes active. That's what this one is for. These voltages here are fancier. These are the power supplies for the phase lock loops inside the analog part of the FPGA. And they have very specific power requirements. In order to run stably, they need their own private bypass capacitors, okay? And the FPGA also has its own separate ground that's specific to these PLLs. You cannot connect these to system ground, right? It won't work. And if you look at the Git repo revision history, you'll see early on I made that boo-boo. Don't do that. Ground PLL1 is specifically provided on a pin so you can hook your bypass capacitors up to that pin, or PLL1. Same thing with ground PLL0. All right, so there's two PLLs. Each one of them needs to be bypassed separately. These values for the resistors and the capacitors are given in the data sheet. It simply says, do this, so you do this. All right, put 100 ohm in here off of the 1.2 volt supply, bypass caps, and ground it accordingly. That's how it got the way it is, because they said to do that. A bunch of ground pins all represented here by one signal on the schematic. All of those go to system ground. Now that leaves us with the reset pin here, which you simply take to ground. And then when you let it float, you'll have reset the FPGA, just like a microcontroller or anything else like that. Which leaves us then with the configuration pins. You recognize this as serial data out, serial data in, serial clock, and slave select from a standard SPI interface. These pins I hook up either directly to the Raspberry Pi, or you hook them up directly to the flash chip itself, within which it holds the program that the FPGA will boot itself out of. Okay? Now there's something funky going on with these diodes. I'm going to record a separate video on exactly how these diodes are used, why they're there, and how the switching back and forth between programming an FPGA out of a flash chip versus directly from a processor like a Raspberry Pi really works, and why did I do it this way? That'll be a whole discussion unto itself. And I want to get down that rabbit hole right now. For now, program it using the flash chip because it's more straightforward to understand. And this part of the schematic down here in the lower right corner, it says insert jumpers to program from a Pi or from the flash. Insert J7 to power the FPGA from the Pi. That's fine. Insert jumpers. Okay, so what you do here is these two here from pins 5 and 6 as well as 7 to 8. If you put both of the jumpers in horizontally, what happens is the FPGA will be programmed directly from the Raspberry Pi. And you have to write a special program to do that, which I'll explain some other time. If you put them vertically like this, then the FPGA will boot itself out of the flash. So when you put your board together, what that means, if you're going to use the flash chip, you put a horizontal jumper here, horizontal, and then you put a vertical one here, a vertical one there, horizontal, 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 horizontal. Okay? Now, I don't make that super clear in the schematic drawing here, but if you read the data sheets and you really understand what's going on, I hope more obvious. Okay? But that's what this little thing means down here. For now, just follow the vertical orientation for these two jumpers here, 5-7 and the 6-8 jumpers. The rest of them are all horizontal. The only thing that happens when the jumpers are in J6, okay, is it allows you to plug in a Raspberry Pi to one of the Pi headers, and it allows the Raspberry Pi to use the standard Linux application to download code into the flash ROM that's on your board, which is this component right here, U4, okay? Due to the way these jumpers and the diodes above work, the Raspberry Pi, when jumpered with the vertical ones, can directly program, can write and read and erase and manipulate the data in this flash if it wants to, okay? If you pull out every one of the jumpers right here in J6, then the FPGA can boot itself directly out of the flash, but the Pi is completely disconnected. So, as I explained earlier, one of my goals was to be able to run the FPGA as naked as possible without any interference from any outside components. So, in theory, you can pull out every one of the jumpers out of J6 here, and you can power up the breakout board, and the FPGA will boot itself from this flash, and all these other pins will not be committed to anything at all or connected to anything at all, okay? Same thing holds true. Here's the LEDs and the switches in this design. These are merely connected up to these various signal names coming out of the FPGA. If you don't solder them in, you're not interfering with the pins from the FPGA, all right? This USB connector is marked as for power only. I used to have a USB, like a mini B connector on there. This is a USB-C connector. And in the video, when I assemble the FPGA breakout board, I put the USB-C connector in there and I power it up and draw like 3 amps out of it just to make sure that things are good. I mean, this breakout board probably uses like 110 milliamps on it with all the LEDs on. I mean, it really doesn't use much power at all. The most power consuming thing on here is probably the SD card over here. If you're programming it, it's going to take some more power. But USB-C is far more common these days than a micro or a mini B. So I thought I would upgrade this when I went to Rev 4, and it works nicely. I like it. I hooked up these LEDs to some pretty much arbitrary pins, as well as these switches, so that you can use them as indicators and input bits if you want to. This flash chip here is, I chose this specific one, the AT45 series. This is very common and widely used for booting up FPGAs. The only rule when it comes to actually picking which one of these many flash chips you can buy from many vendors is that it understands a certain very specific subset of commands that the FPGA knows how to use. Basically, it has to be able to read data out of the flash chip. So you can't just stick any old one in there. It needs to support a specific read command and a power down command or something like that, which we can talk about in the programming the FPGA and what it needs from its flash. The simple fact is it needs an SPI flash that can go at least at 1.5 megabits or something like that, and any flash chip will run the data rate. It has to run at 3.3 volts because that's what this particular FPGA needs on its SPI interface. And the data sheets for the programming recommends that you use 10K pull-ups exactly as I've shown here. The data sheets for the flash chip says to throw in some bypass caps along the lines of this, which I have also then done just because they say to do it. Write protect. If this is grounded, then this flash would not allow itself to be reprogrammed. I just hardwired it up to 3.3 volts. I could put another jumper in there if I really wanted to, but no. Why bother? For this purpose, all I'm ever going to do is use this for, testing and evaluating and things like that anyway. And the FPGA is not going to write into it. You could, if you wanted to, create an FPGA application that after it boots goes in there and modifies the contents of the flash if you really wanted to. Because I've tied this to 3.3 volts, so be it. If you don't like that, then don't do that, okay? And if you really don't like it, you can just go hack up the design. That's why I share the schematics and the boards and everything else. So you can put jumpers wherever you want them and hack it up for your own projects. Down here are two identical Raspberry Pi headers with all the same signals on all the same pins. As I explained when we were looking at the picture earlier, you plug the Raspberry Pi into one of them and the other one exists so you can put probes on the pins that are otherwise covered by the cables. These here are the J1 and J2, the north side, south side, big headers up here, J1 and J2 there. Okay, here's the two Raspberry Pi headers. Here is a power jumper, and the reason that's in there is it allows you, if you put the jumper in J7 here, it allows the Raspberry Pi 5-volt power to flow into the FPGA board, and you can power the FPGA board that way. And you don't even need to solder in this, USB connector if you don't want to. If that's all you're ever going to do, you don't even need this part up here. You just leave J7 in. The other thing it'll let you do is if you have USB-C here and you put this in and you connect up a Raspberry Pi, then the USB-C here will power the FPGA board and the Raspberry Pi through the 40-pin Pi cable. All right? You never want to power both the FPGA board and the Pi independently, especially from different power supplies. You just don't ever want to do that with this particular product. There's no diodes and protection safety things in here if the power supplies are at different voltages or anything like that. Don't do that, okay? That's not what this is for. This is very simple. You're either powering everything from the Raspberry Pi or you want to power everything from the FPGA Breakout board. Pick one. That's how you want to do it. And that power jumper is this guy right there. Okay, insert the power from the Pi, or vice versa, power it backwards. So nothing special about these headers here. They just simply are pinned out to connect to every one of the I/O pins that you see up here that are otherwise not dedicated to anything specific and custom. And by that, I mean this oscillator right here. So I want a 25 megahertz oscillator. You can buy different frequencies if you want them. There's a whole bunch of different sizes with the same footprint if you want. And I'll hook this up to what we say IOB82. And if you look closely, IOB82 I think is right over here. And you'll see it's a G-bin. So remember, the idea with these G-bin pins are that these are specially routed to everywhere inside the entire FPGA so that if I wanted to, I could connect that clock input on GB4 to any LUT anywhere in the entire FPGA as efficiently as possible. And as you look closely, you'll notice these G-bins there, and there. On each of the 4 banks, there's 2 G-bins. Okay? Those are the 8 G-bins for the entire FPGA that we saw when we were looking at the data sheet earlier. These are special pins, okay? I put the clock on there because if you want to use the clock directly and not use a PLL, and you want to just use the clock to, trigger any circuitry that you're going to design to run in the FPGA, you want it on a G-bin. These pins down here have special names on them as well. Notice it says CB cell 0 and CB cell 1. I did not do anything interesting with these. I just ignored these. What this has to do with is a really cool feature that allows the FPGA to boot from any one of 4 different programs in the flash chip here. So I can program 4 different application programs, or whatever you want to call your firmware that configures the FPGA. I can put 4 of them in this flash chip. And then I can toggle in a binary number on these 2 pins here and tell it, when you reboot, run program 0, program 3, whatever. Okay? So that's kind of a neat feature, and I want to play around with that at some point. Hopefully these pins 103 and 104 are not hooked up to anything too wonky. Let's look at this picture down here. 103 and 104, 102, 5. Here's 104. Where's 103? Does that say 103? Oh, this is IOB 103. Pins 63 and 64. Ugh. You got to be careful. We'll talk about why these are numbered so weird. Here's 63 and 64 over there. I find this incredibly annoying. The fact that the pins have names that have numbers in them that are different than the pin number on the chip, and then when you configure it, you refer to the pin number, but you're really working with the name of the signal. We'll get there soon enough. Why is IOB 95 on pin 60? Why didn't they call it 60? Or yeah. This is one of the things you have to decide that you're going to always just use pin numbers, or you're going to use their kind of functional names. All right. I'd love to hear your opinion. Please chime in the comments below. Should I religiously just use the pin numbers for all this, just FPGA 4, 5, 6, 7, or should we use these logical names over here? If you look closely, you'll notice that you've got T, B. Right, all these are IOBs. These ones on the left are all IOTs. These are all IOR and IOL, which I suspect means top, bottom, left, and right for the 4 IO banks around the outside of the chip. Okay. Now these ABs that are on the left bank over here in IO bank number 3. These suggest very strongly, notice there's a 2A, 2B, 3A, 3B. These other ones just have a 109, 110, 111. There's no ABs over there, is my point. These things here, I believe, are ABs because they're paired up and they're intended to be used if you engage, dual data rate and LVDS and stuff like that. So these are paired together, and as such, they can have special traits that can be configured, okay? I'm not going to get into that with this particular project, but it is because this one is logically different than the other 3. I decided to use the role-based name IOL2A as the signal name in the schematic rather than the pin numbers, which interestingly are the way you configure the darn thing, is by, as we'll see when we write our first program and we look at all the details, you actually say, I need pin 7 connected to such and so, rather than saying I want IOL4A connected to such and so, okay? All the vendors basically do the same thing, and yes, okay, so you need like a spreadsheet. You need to keep track of both of them at the same time so you get all this stuff straight. It's not my fault. Okay, I'm just saying. This is a very common trait amongst a lot of FPGA design projects. Okay, so that's all we have on the board. What else? I guess we can talk about the power supply, and I guess I didn't mention the SD card yet. Here's the power supply, 2 analog linear regulators. This thing uses almost no power at all. So really cheap, really simple, 1.2 volt LDO and a 3.3 volt LDO, both connected to the raw 5 volts that comes out of our USB connector, and we're done. That's the entire power supply. What did we not talk about yet? Okay, so the SD card. I just added this, and I've never tested it. But somebody on the Discord said that they downloaded some SD code that they found on the net and ported it over to run on my Breakout board, and it works. So on that authority, it's fine. I have no reason to doubt this person. They seem to be really working and doing all kinds of neat things with their version of this board, and they've done some tweaks and things, and we've been talking, among other things like that, the clock pin that I keep bringing up, which is not really the end of the world, but it's something of interest, okay? So what do we do here? I pretty much arbitrarily chose a bunch of pins here that I'm going to connect to the SD card. And because this is SPI based, do not confuse these SPI pin names, okay, with the SPI bus up here. These have nothing whatsoever to do with each other. Nothing at all, okay? And it will not, cannot, will, absolutely will not boot from an SD card. The FPGA protocol that it uses on the SPI bus cannot work with an SD card. This SD card SPI interface and the flash chip SPI interface, not even close to the same thing, okay? Other than the names of the pins, nothing else is going to be compatible. And that, I totally agree, is a total drag. It would be so cool if the SD card could squawk whatever it is this little flash chip does down here. And that would be really cool. You just pop in an SD card. You can use that to program the darn FPGA, download into the flash to boot the FPGA out of, I should say, rather than all the rigmarole with a Raspberry Pi or some other, programming device and screw around with all these jumpers. And on behalf of the entire FPGA world, I apologize to any newcomer that thinks we're crazy. All right. Reality is the FPGA and this flash chip came decades before the SD card interface was ever invented. So they decided to, in my opinion, screw up the SD card interface. There's all these different versions and stuff like that, and protocols and handshaking and stuff that goes on when an SD card boots, none of which is supported by the good old, simple to use single chip flash memory chip down here. So no, these two are not compatible. Darn it. Okay. Couple of bypass caps that we float around the board to make sure the 1.2 and the 3.3 volt power supplies are stable, mostly around these power pins up here. All right. So there's the design, and I hope that I've just beaten the point enough to make sure that everybody follows along. Why am I doing this? Why didn't I just use something else? The closest thing to this would be the Icestick from Lattice. If you go down and look at the schematic for the Icestick, which I'm sure we can, actually I might even have a link to it down here somewhere. Well, there's the family page. If you wander around in here and you say, oh, I don't want to build this thing, I'm going to go get one of these other ones. Why bother? Well, there's a reason. The Icestick, okay, means these, means those, blah, 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 design resources. So you can actually download their own software. You can, what's all this thing? Reference design. So inside here, there's some, sample code and schematics and hints and rules of thumb. Oh, here you go. Development boards and kits. Here we go. And we can have an eyeball at those, and maybe we'll come up with some better ideas as we go along. I shoulda, coulda, woulda. This thing here is the closest thing to what I've done. I guess and now there's a whole bunch of boards. A lot of these are pretty new. Some of these are pretty much not available. And you can see some of these are the LP, and there's another HX. This one actually looks like maybe it's similar to mine. And it has a board, a regular big board with headers all the way around it. But at the time, I was only looking at this, and this Icestick, when I bought it, was $25. Now it's like $50. Now, when you get to the point where the cost for an eval board, here it is, it's $50. It's the same as just building one. I kind of start thinking about building one. And so the main reason we're even here looking at this is because if you look at the schematic of this thing, well, we don't even need to go that far. See this block diagram? 1, 2, 3, 4, 5, 7, 8, maybe 16 pins. Then there's another set of headers over here. There's a PMOD header, which has 6 I/O pins. Out of the 144, they pinned out about, 10 or 20 pins that I can do what I want with. All the rest are either not connected at all or connected to a whole bunch of other things on this board that I don't want to use. So therein is the problem. Now, I have one of these, and it works. It got me going. I'm very happy about it, especially for 25 US. Get one. It's definitely an easy do. However, if you need to hook up 100 I/O pins to something, you don't want to do that with this board. It's just not going to happen. If you really need to have all the pins of this socket here uncommitted, you got to go your own way. And thus I did. Now, when we're looking around in here, what's this ICO board? So some of these are actually pretty cool. Of course, this is 89 euros, and it's got funky connectors. Oh, that's a big boy. That's a, what is it, an HX8K with a ball grid? It was with 8 megabits of SRAM. That's kind of neat. All right, but, you know, you'll have to go in here and look at all the schematics and everything else. Do step files, yabba Rev 2, Rev 3 documents, and we'll be here 20 minutes. Schematics, PDF, I don't know, let's just see what they got. Okay, what do we got here? Oh, this is an unplanned rabbit hole dive, if I ever saw one. What do they got? They got RGB LEDs. They got, what is this thing? SMD socket, 90 degree. Those are right angle pin headers or something. As again, you see the 4 banks. This is obviously drawn up with Altium. It looks a lot like an Altium schematic. There's a do not populate this part for whatever reason, bunch of grounds and whatnot. I don't know what that was. What's this thing over here? A0. That's a RAM of some kind. Here's your flash boot. What's this? Another one? BDD-OE. Oh, this might be like an I2C flash. That's kind of a trend now as well. Oh, let's throw that on the board. And again, it starts taking up all these pins. Here's the same kind of a drawing that I had on mine. You can see down here the 2 PLLs with their own grounds, and the same thing down here with the 100 ohm from the 1.2 supply. I'm looking closely to make sure they agree with me, because this is one of the things I do. If I ever see another board and it doesn't look like mine in some way, I go back and ask, gee, did I misread something? So but you're going to see the same thing there. Why? Because the manufacturer recommended you do it that way. And there's, how do I know better? Why I shouldn't mess with that, right? And we get some power pins over there. And there's, these 4 headers. What's this thing over here? Oh, that might be a, what is that? A 40 pin. Wow. Did they do a Raspberry Pi? Yes, they did. Wow. I wonder if they stole this from me. What year did this come out? Well, looks like maybe I stole it from them. They say 2016. So, all right. So this was available, but it has those wonky headers that I didn't really want to deal with. Do I want to source, I guess these could be used for edge cards. But even if I built a system, design something based on this board, and I decide, okay, I want to move this on and make a custom board having all these same parts, I'm stuck with this ball grid, which is not always the easiest thing to put in. This is probably the RAM chip there. And these are going to be PMOD compatible headers, I'm sure, a little prototyping space. All right, whatever. So you've got a bunch of these boards. Sure, you can use them. And as you just saw, I picked one at random here. Here's a tiny FPGA. All these, you're going to open up the same overall PLL bypass, probably the same analog power supply, and they'll probably power themselves off a USB supply or something like that. The Olimex, I think I looked at one of these at one point. That's a crazy good price. I think these were out of stock a couple years ago when I was looking, because this isn't too bad. But they do use a lot of the pins up for an SD RAM here. I'm sure that's what that is. For whatever reason, I decided not to go with this one. Yeah, so this is, well, it's a ball grid. So if I decided to, integrate into a custom board, I had to deal with this ball grid. And I'm still kind of concerned about doing those by hand. I'm sure I could figure it out, but I'm still more of a fan of the gull wing style headers like I have on a chip like this, these quad flats. way more friendly to the weekend warrior hobbyist, okay? So that's how this particular design evolved into being, right? It was, I want to know, could I build something from scratch if I wanted to? Certainly doing that is going to answer that question, yes or no. The second one was, can I get an FPGA breakout board with as many pins as possible, completely uncommitted? And the answer is sure, if you build it yourself. Not, you can get anything you want. Another one was, I wanted to experiment with this Raspberry Pi to directly program the FPGA. And as far as I knew, nobody had that available. They always wanted you to program a flash and then boot the FPGA rather from the flash. All right. Some people were playing around with jumpers and other types of things. There's a thing called a cat board out there that's open source that is pretty cool as well. And the guy who puts that together has got a video of himself putting in a ball grid using a heat gun for a paint stripper. And it worked. So, that guy was the one that made me think that I had hope someday that I'd be able to get ball grids in as a hobbyist without too much effort. But anyway, that's what he did. But if I recall correctly, the cat board, let's see here, had a SD RAM on it that hogged up a lot of the pins again. All right, so he's got some animated thing. Yeah, there's an SD RAM right there. So let me see. Zoom out here. Where's the image gallery? One of these videos is himself putting the thing in with a heat gun. If you play around, in fact, here we go. Ball grid mounting. Yeah, watch this thing. You saw me Google for it. You know what to do. Go in there, look at this guy, see what he does up there. And nowadays you've got all these too. But, how many pins you got in here? 40? All right. Now I got 100. Find me one with 100 pins broken out. All right. And why do we need 100? Well, it depends on the project you're working on. Where I'm ultimately going with this is I want to build a board that plugs into this header here. And it turns out that every single signal on this header needs to be used. It's going to go into a Z80, an S180 CPU board with like a megabyte of RAM. So I need all the address and data lines and control lines to interact with that CPU and the RAM. And it turns out there's exactly the right number of pins here in revision 3 of this board. I had to move a couple of signal pins that used to be up here down to here, like these two push buttons. If you go back to Rev 2 and Rev 1 of this design, some of these things used to be connected into double purpose pins up here on this connector. All right, now they're connected down here along with the LEDs. Okay, turns out that a PMOD is a pinout standard if you're into FPGAs. I decided, there's no reason not to. When you're assembling this board, if you want to, you can just cut off the header here, put a right angle one in there, or whatever you need, and it turns out that these are compatible with the PMOD standards if you want. All you really need for PMOD, by the way, is that you have to have 3.3 volts on these two pins, ground on these two pins, and the other 8 can be used for signals. That's the PMOD, okay? And they're, of course, 3.3 volts. And if you buy PMOD products, there's a single port PMOD and a double port PMOD, and you can't use a double port on here. Double ports are like if you have two PMOD headers that are specifically right next to each other, like you saw on that Alamex board. If I still has it in my history somewhere. Oh, maybe this one up here. Ico. Yeah, see how there's these two here? Now, I don't know that this board specifically is compatible with a double PMOD. I'm sure it is, because that's what you would do if you built this sort of thing. Some of them have, one board that needs two PMOD headers next to each other, and the spacing in here is what I'm getting at, means something, okay? So you need to have, I don't know which end is power and ground, and I'm going to just guess, power, ground signal. And you got power, ground signal. Or it's flipped around the other way in a mirror image, and the power and the ground are on the other side. But you know what I'm talking about. My board does not have two of them next to each other like that, so you can put a double PMOD jobber in there. Okay, but if you wanted, you could put a single one in here and not have too much trouble. And if you know how to use KiCad, you can always hack up the pins on here and change it to whatever you want, or stick one over here, or, that's why I give these things away, all right? You can run with these, run like the wind with these things. So let's have a closer view when we wrap up for the day at what's going on down here. Why are these things italicized, sometimes not, okay? So if you zoom way in here, you see these green lines that sneak around here? These go to the SD card. Another difference between Rev 3 and the Rev 2 of this board is this SD card used to originally hook up to the PMOD pins up here. And because I found out that I wanted the entire connector to be uncommitted up here, I rerouted the board. The main difference between Rev 2 and Rev 3 in this design is that the SD card pins don't go up here. They go down south, okay? So if we look closely, any pin with an italicized font has two tracks. The red ones over here on the top of the board run directly over to the FPGA. These green ones, as you just saw, wrap around here and go up to the SD card, all right? So if the pin number is in italic, it means be careful, because that could be committed to something on the FPGA board, on the Breakout board. If it's not italic, like these over here are regular, square boxy jobs, that means this pin is, unadulterated, goes directly up here, as you can see, to the FPGA, and there's absolutely nothing else connected to it. All right, so if you're just clowning around, you're just poking around, and I want to hook something up to one of these pins, you can know, all things being equal, be careful, don't use this pin, because 110 might be somewhere else. So if you track this up here, you can see, oh look, there's a VIA right there. And it goes to an LED over here, all right? So if the LEDs are in, beware that, you've got, some circuitry on there that could be interfering with an otherwise pristine, virgin signal coming out of the FPGA up here, all right? So that's what it means when these things are slanted. The flash chip uses pins that are committed and dedicated to flash booting from the FPGA anyway, and those pins also run to this header over there. Like I said, we'll sit down and look very closely at what goes on when an FPGA boots at another time. But the short of it is, and as I had mentioned earlier, this flash is wired in so that the SPI pins are connected to the FPGA so that it could self-boot directly out of here. Once you got the flash programmed, it will be able to do that. These headers are necessary to put jumpers on here. If you're going to use a Raspberry Pi to program the flash, it uses these signals here. And we'll look at that when we look at how to program, or how to download a program, I should say, into the Breakout board at another time. Now, if you use a different Breakout board, 9 times out of 10, 99.99999% of the time, you're not going to have a Raspberry Pi header over here to program this flash chip. That's just not going to happen. What they do is they have a couple of different ways of making this happen. Very common, what they do is they put a little CPU on board that has a USB header on it, so that you can just plug in a USB cable and it says, "Hi, I'm a programmer for flash chips," and you run a little app and it'll download into the flash for you. But if you do that on a hobby project, you then have to pay for that whole Arduino-esque microcontroller that has no other purpose than to program this flash and solder it in, waste the power and the board space to host the stupid thing. A very common one to use is one of those FTDI chips. It's incredibly common to use those for programming these flashes, or even using them for JTAG programming. They're just really, really popular for that. I just didn't want to spend, the money on more money on a FTDI chip than I'm spending on the whole flash, or in some cases the whole FPGA. These used to be pretty cheap, with COVID and all this garbage and a shortage. The price has gone up a little bit on these FPGAs, which I guess in closure leads us to one last little note. Why did I choose this FPGA and not some fancy modern one? Because 4 years ago, they didn't have the fancy modern ones with the built-in RISC-V cores and things like that. And if you even try to go get one of those, you're not going to get it for $9. Or when I started this project, these were only $6. So, if you want a lot of I/O at rock bottom prices, this is a pretty reasonable thing. And as we get into the programming of it, and designing the software and all, you're also going to find out that each vendor has their own software, which is, in my opinion, I don't use Windows. So Windows is very widely supported for those things, and Linux is not so always easily supported. And even when it is, they do a crappy job. It is just a nightmare to get that stuff to work. No, I'm not going to use virtual machines, cloud crap, and every other foolish thing. No, 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 no. I need software that when I install it, I know that it can run today if I use it today, and 10 years from now, if I want to do it again, it will still work, okay? If you go grab rando cloud stuff or vendor tools that are upgraded every 6 months and new licenses and all this endless malarkey, what happens is all your build files and everything else, you need to upgrade this, you need to port that. It could take 3 days to just recompile the same thing without any mods after the world has decided to change everything when you weren't looking. I can't stand that. Not my thing. We're going to use what are called the Ice Storm development tools. I've been using them for 4 years. If you click here, I've been using these for 4 years. They all work fine. I'm only now upgrading to this new version of the PNR tools because it was not available. I don't know what I couldn't get it to build or something 4 years ago, but today it's a standard tool. The old one used to use a Arachne. The new one's Next PNR. Next PNR works. It runs a lot faster than this one, and I think it does a better job as well. The newer versions, all in the Ice Storm and Next PNR, generates, when you compile a program, and we'll look at this when we actually write some code, depending on the quality of the tools, it can use less LUTs, and it can therefore run faster if it does a better job. Just like a compiler on for any CPU. You write a program in C or something, and you got a crappy compiler, it's not going to run so fast. It'll use more resources. And an FPGA, that means it's going to use more of the fabric of the FPGA. And not only could it run more slowly as a result, it might not even fit in the FPGA. Unlike a computer program, if you cannot optimize an FPGA program well enough, you can't even fit it in the chip, right? I suppose the purely software analog would be if it used up too much memory and it would then not load, that kind of a problem. So, yeah, the quality of these tools are going to be a lot more apparent when you program with some HDL than it is with a regular C program when you're running it on Windows or Mac or Linux or something like that. A slight speed variation over there won't make so much a big deal. But on an FPGA, it could be all or nothing when you're dealing with the limits of the chip that you've chosen. We'll stay away from that domain of problems, but you want to know as we go, I'll point it out, where the issues can come up if you make design choices that you think, oh, it doesn't matter, I use method A or B, and we'll look closely at what happens, and holy cow, you need to pay attention to what's going on if you choose poorly. So anyway, my point is that next PNR from completely non-scientific random, they'll build the same app with two different versions and see what changes. Well, some minor issues did change enough for me to notice between these two apps. The most obvious one is that NextPNR just runs much faster, which is a very pleasant experience. And the secondary note is it does do, apparently it does do a better job than the old Arachne did. Okay, so, and as I look in here, I can see that I install both anyhow. To run these on here, do this on a Raspberry Pi, which is pretty darn simple, straightforward. This, you can't get simpler, people. If you buy an FPGA eval board like a Spartan 3E evaluation board that I got, I don't know, at this point like 15 years ago. By the time I got an LED to flash, I can't tell you how many weekends of frustration went by. And I can assure you it takes much more than that to make it go. And it takes much more than this to get a graph of a simulation to go on the screen as well. So anyway, next time we'll look more at programming the FPGA and bring this thing to life on this breakout board. And if you look closely inside here, and these are the example programs for this breakout board, of course. If you look at what have I got? I got a couple of other repos in my test programs are here. Bill of materials are there. Oh, I really should put another link in here at some point. Oh boy, if you go to all my repos and you, let's see here, here's my repository 70. And they're not all mine. Some of these are cloned. Here's the S180 board, by the way. So spoiler alert, this is the board that I built that needs some work. I put a warning in here. Don't build this, because one of the guys in the Discord said, I need to do something different on this connector. I think one of the footprints is even poorly done. Oops, underneath this CPU here. So I need to make some minor revisions. But my point is, this connector here is supposed to connect to, is supposed to plug into this top connector on here. All right, so ultimately, that's my main motivation for revision 3 of the breakout board, is to go along with this, is my point, while we're tiptoeing through repos here. Okay, so Verilog example, Icestick examples with Icarus. These are some HDL programs. This is obviously Verilog. And what do we got here? You see how it says Arduino, Icestick, and 2057. My point is, if you look at these repos, and I'll start, organizing these things a little bit better as this evolves, I talk about how to use the same code on 3 different boards, all right? How to configure your various things, how to compile them, and you'll notice it's the same program that I have in my breakout board. But this repo here is specifically set up to allow you to compile the same code for either the Icestick or the Arduino or my breakout board. All right, so don't freak out and think that you're hemmed in and we're only going to be talking about my breakout, but this is really about all these other ones as well. And the Arduino is a completely different kind of FPGA. Same manufacturer, will use the same Ice Storm development kit, but it is a different FPGA. So it's intended to be used for different types of problems, okay? And you'll note, what's cool about it is the same code can run on all these different boards. As I've said before, the Verilog and VHDL languages are so incredibly portable as to, I'm shocked. Quite often you're like, oh, here's some program I wrote, and you try to compile it in your life as a pure and with no doubt living hell to get the thing to even compile, not to mention run. But Verilog and VHDL are so specific that like I have never found a case where, unless the person writes a piece of garbage, anything that basically runs on any one, your Xilinx or your Altera and, whatever the build environments you're going to use, they work on all of them. Okay. Now there are vendor specific enhancements that can get in the way of portability, and we'll talk about some of that as well. And we will do it ourselves. All FPGAs require you to use some form of vendor-specific features because of the chip itself. How in the world does the program know that pin 103 over here is used for some purpose, or any other pin on any other chip might, it might not even have the same physical package. You might have a 208 pin quad flat or a ball grid or something. So clearly, once you get to the point where you're dealing with the physical chip itself, and in the simplest case, it's merely identifying the pin number that a signal has to flow out of or into the actual physical chip, that is going to be more vendor specific and even chip specific within the vendor. Okay. But when it comes to writing a little program like a counter that flashes an LED, all that code is going to be really portable. So, I mean, I honestly, I am giddy with excitement over that fact because of how many times that I have been let down with portability in general in almost every other language on every other machine I've ever used. Okay, this is really good when it comes to portability. If you separate, all the information about the pin numbers from everything else that you're going to do. All right. So I hope this was helpful to let you know what this thing is, why it is the way it is. We start sitting down and looking at the code, and we start connecting things up, and we want to, hey, I want to light up an LED. Well, now look down here. Well, if you want, this top LED diode 3 here, well, that's 118. If you look at the schematic here, and I put these on here. I stole this whole idea of putting these numbers on here. My Spartan board from Xilinx did this, and I'm like, this is genius. This is a lot better than having to go back to the printed documentation to figure out what is connected to this LED here. Pain in the butt. Here, front silk on the front and center here. Okay, so in order to turn on this LED, you take pin number 118. If you look closely at this track, that's why I went back here, and we'll see this IoT 177, and see it goes up here. I should have used the highlight. If you click this and you hit what, T? No, H? No, I'll probably break my... I forgot. There's like a select track mode in here. Whatever. You can see clearly that it goes to pin 118 over here is my point. Okay. So I put down the pin numbers here so they're real obvious when you're looking at the board. I need to see this LED go on. So use pin 110 and so on. All right. And that's the case all the way around all these. These are the FPGA pin numbers that correspond with the pin header there. 105 and 102 are the pin numbers that these switches here are connected to. And if you're going to hook up the SD card, which is on the bottom of this thing, if we zoom way out here, see the SD card down there? Those guys, the pins that are important of interest there. The card detect is hooked to FPGA pin 125, slave select 117, and so on. All right, and this is just so wonderful when you have that in your face. Just the same sort of thing going on over here with the Raspberry Pi. All right, so you don't have to keep looking back at the printed manual. I love it when people do stuff like this. You design a board, please do me the same courtesy. So there we have it. There's the motive for why this is the way it is. And the reason I'm focusing on this board versus any other one is solely because I want as many pins as possible coming out of this. And while this particular series of videos, I want to focus mostly on Verilog programming, You obviously have to eventually connect it up to the real world through the pins and the schematic of the eval board, and whatever your other surrounding components are going to become relevant. So we need to understand that. And ultimately, what I want to do is use this series as an introduction to this whole process for people that want to play around with the Z8 S180 board that plugs into this header over here. If they have not ever dealt with FPGAs before, or are rusty, or I've done something totally screwy that they've never seen before, they can refer back to this particular series and see what the heck is going on, what I was thinking. All right, so thanks for watching. I'll see you on the internet.